Hello, and welcome to our discussion of the method of undetermined coefficients. Here is our goal. We want to find a way to solve the problem f double prime plus a1 f prime plus a0 f equals g without using variation of parameters. So here we have a second-order linear constant coefficient differential equation. It is non-homogeneous, and we do not want to use variation of parameters because we do not want to have to evaluate integrals. As we've seen, evaluating those integrals and variation of parameters can be time-consuming or difficult or simply impossible to get an explicit antiderivative. So we will develop an alternative method that works for some special kinds of non-homogeneities G. And to see where this method comes from, it's useful to zoom out quite a bit and view things in terms of more arbitrary linear operators and vector spaces. So let's suppose we have vector spaces x and y, and A is a linear operator from x to y, and G is a fixed vector in y. We want to solve the linear equation A on f equals G for some vector f in x. Zooming back in for a moment, our operator here is A on f equals f double prime plus a1 f prime plus a0 f. Now suppose we are in the following happy situation. There is another vector space z and an operator b that goes from y to z with the property that b on g is equal to 0. Then if we are able to solve our original problem a on f equals g, we also must have b on a on f equals b on g equals 0. So when we are looking for solutions to our original problem a on f equals g, it suffices to restrict our search to vectors f and x such that b on a on f equals 0. That is, we are looking for f in the kernel of b times a. And our hope in doing this is that the equation b on a on f equals 0 will somehow be easy to solve. I think we can all agree that we would rather solve a constant coefficient homogeneous problem than a constant coefficient non-homogeneous problem, even if the homogeneous problem is a differential equation of much higher order than the non-homogeneous problem. In other words, the operator b times a may be more complicated than just a by itself, but the equation b on a on f equals 0 will be easier than a on f equals g. So let's zoom back into a very particular example that will illustrate this method. We want to solve f double prime plus f equals e to the 2x, ideally without using variation of parameters. So here, our operator a is a on f equals f double prime plus f. This is a very familiar operator. We know that a fundamental solution set for a is e to the ix and e to the minus ix, or another fundamental solution set is cosine of x, sine of x. Now, we want a differential operator b such that b applied to e to the 2x is equal to 0. That is, what equation does g of x equal e to the 2x solve? We think for a bit. We look back at our old notes, and we're going to guess we should put b on g equals g prime minus 2g. And indeed, we can check, plug e to the 2x into b, so derivative on e to the 2x minus 2e to the 2x. By the chain rule, that is 2e to the 2x minus 2e to the 2x. That is 0. So we will look for solutions f to our original problem a on f equals e to the 2x that satisfy b on a on f equals 0. That is, we want to solve 0 equals b on a on f, and that's derivative minus 2 times derivative squared plus 1 on f. Let's not bother expanding this operator ba and foiling out all the partial x's. Instead, we can just find its characteristic polynomial directly. The characteristic polynomial of ba, chi ba of lambda, is lambda minus 2 times lambda squared plus 1. And this is nicely factored already because I didn't bother expanding ba. And to be clear about how I read off this characteristic polynomial, I looked at ba on f, and every time I saw a derivative with respect to x, I wrote down a lambda. So the roots of this characteristic equation are 2 and plus or minus I, all of which have multiplicity 1. And therefore, if b on a on f equals 0, we can write f of x equals c1 e to the ix plus c2 e to the minus ix plus c3 e to the 2x. And any solution f to our original problem a on f equals e to the 2x must have the form above. So we just have to figure out what c1, c2, and c3 are. And I think we can already expect that we will not be able to determine precisely what c1 and c2 are, because c1 and c2 are coefficients attached to the fundamental solution set for a, and in our general solution to af equals e to the 2x, we should have an arbitrary linear combination of functions from the fundamental solution set. So what do? The only thing we know that this form star for f does is it has to satisfy af equals e to the 2x. So let's plug star into our original differential equation. We get e to the 2x has to be equal to a on f, which has to be equal to a on c1 e to the ix, plus c2 e to the minus ix, plus c3 e to the 2x. Linearity says this is c1 times a on e to the ix, plus c2 times a on e to the minus ix, plus c3 times a on e to the 2x. And that just collapses to c3 on a e to the 2x. Because, of course, a on e to the plus or minus ix is equal to 0. So we need e to the 2x equals c3 on a e to the minus 2x. And then we just calculate what a on e to the minus 2x is. We do the derivatives. This becomes c3 times 4 e to the 2x plus e to the 2x. That is 5c3 e to the 2x. So I want e to the 2x to be equal to 5c3 e to the 2x. That means I need c3 equal to 1/5. So my general solution is then f of x equals c1 e to the ix plus c2 e to the minus ix plus e to the 2x over 5. And if you prefer to use the other fundamental solution set for a, the real valued fundamental solution set, you can write the general solution in the form d1 cosine of x plus d2 sine of x plus e to the 2x over 5, where now d1 and d2 are different scalars.